In a way, it's just fate. And, you know, I still do design buildings in normal situations, art galleries and offices, just like lots of other architects. But a stroke of luck came my way in 2004 when I noticed the announcement of a design competition for a new Antarctic research station for the UK on the floating Brunt ice shelf. And although I ran a relatively very small architectural practice, it was a unique competition because it was one of those rare occasions when nobody else could put up, oh look, I've done 6 of those before. So it was what we call a completely level playing field. We were very lucky because we teamed up with some engineers who, amongst their ranks, they had an engineer from the USA who had worked on the US Antarctic program for a number of years, and he gave us the kind of basic expertise we needed to start with. And all of a sudden, there we were, competing to design an Antarctic research station, and through that process we won the first one. And then, of course, once you've won the first Antarctic research station, suddenly, from nowhere, you become an expert. And so other countries have sought that expertise out to help them with their own projects. So from the British station, we've ended up doing work for Spain. We've done designs for India and South Korea. And we're now working with the USA on a project in Greenland. So it's kind of mushroomed from one to many. Well, Halley is definitely the most unusual of all of them because it has some very specific criteria that it has to respond to. Not only is it cold and windy, but it's on what's called a floating ice shelf, which is when the ice has flowed off the main continent of the Antarctic and is literally bobbing about on the ocean. And the base at Halley is on that ice shelf, and it's there for a very specific reason, because it's in a fantastic zone for carrying out atmospheric science. But the fact that it's on a floating ice shelf and the fact that the snow is rising in 1 metre per annum gives it some particularly demanding design parameters. So we had to design it so that if that ice shelf ever carved off as an iceberg, you could pull the station inland and keep it safe from disappearing on that iceberg. And then also we had to design it so that it could accommodate the rising snowfall. So what we did is we split it up into modules so that they weren't too heavy, so they could be pulled by big tractors. We put each of those modules onto hydraulic legs, so the hydraulics could be used for the modules to climb out of the rising snow level. And then finally we based those legs on big giant skis so they can be used for pulling it from one place to another. But it's inevitably through that process delivered a very specific kind of architectural expression, which makes it look a bit like a space station, I guess.
And this isn't the first station in that area, it's actually the 6th.
That's right. That's right. The first station was built in the International Geophysical Year in 1957 and was really just a basic timber hut, and the second one was much the same. That in both those cases, the rising snow level and winds and drifting buried the stations very quickly. So having done that, the British then thought, well, if the stations are going to get buried, let's design them to be buried. So the next two, Halley 3 and 4, were designed as tunnels to be buried under the snow and ice. But you only have to imagine very briefly the whole notion of living maybe 20 metres under the ice, hearing it creak as it flows all around you, the stink of sewage and of mechanical plant and petrol, to realise that living under the ice is not really the best solution. So Halley 5 was built as an elevated station, but with the problem that its legs go down into the ice, and so year on year on year those legs had to be extended and the foundations sunk further and further into the ice, so it couldn't be moved. So now we know that there's the risk of it disappearing on an iceberg. We couldn't relocate that Halley 5, so a new station design was needed, hence the evolution of Halley 6.
Tell me about the facilities at the Halley station.
Well, alongside two fantastic science modules which have maximum flexibility for all sorts of different programs researching atmospheric science, we also have some really interesting living spaces, not only obviously things like bedrooms, bathrooms, operations areas, but we have this great big red central module which is the heart of the new station, and in there we have open plan areas for eating, for drinking. There's a bar area, we have TV lounge, we have a gym, we have all sorts of different games, table football, table tennis, all these kind of things. And at one stage we were even thinking of having a climbing wall in there, but it was considered a health and safety risk having a climbing wall next to a bar, so in the end we got rid of that.
And you went to a lot of details in designing this place, and for example used a a specialist regarding the colors, and the walls are made out of special wood. Tell me about that.
Yes. You know, one of the exciting things about this project is up until now, most Antarctic buildings have been designed by engineers and, you know, come up with varying successes in terms of responding to the awesome extreme environment. But architects hadn't been involved. Now here for the first time is a project being designed by an architect, and we're starting to think much more about human factors. So in our station there are, you know, a vast array of measures which are intended to try and help stimulate and care for people, particularly through the dark winters. So that might be ranging from the big scale of the, you know, the nice spaces that we have in our big red module, to having a quiet space for people to read and to contemplate at the other end of the station. And then it gets down to sort of detail levels. For example, you're right, we work with a colour psychologist who'd helped develop a special palette of colours that are all complementary, which help to signpost different places in the building, but also help to promote a sense of physiological well-being during the winter months. And we took that to the kind of next level by asking our colour psychologist to help us with matching up paint colours with fabric colours, with even the colours of timber. And then when we came to our red module, when we were lining the drum around which a spiral staircase rises up to the upper level, we thought, well, what timber should we use there? So we specifically chose the cedar veneer because it's the only one that gives off any natural smell. And it was an opportunity in a place without any vegetation whatsoever to just have a brief hint of the smell of a forest, just to, again, to just help people and to sustain them. And then in the bedrooms, we worked with Philips and developed a special lamp which has an alarm clock attached to it. So you program it for what time you want to wake up, and then daylight simulation lamps gently come on to help you wake up, and those help to rebalance your red and white blood cells and just maintain your biorhythms through the darkness so that you continue with your normal working day, rather than finding all of a sudden that you're losing an hour per day, and instead of working in the day you're working in the night. So there's a series of big and small measures just to help to sustain people.
How are the buildings insulated and heated?
You know, the insulation is absolutely a crucial part of the technical performance of the building. And we had our panels made out of glass fibre, but we have around 220 millimetres of insulation. It's a closed cell foam insulation, and it just gives a really, really excellent level of thermal performance. So that as well as having that level of thermal performance, we also designed a system which by the panels really lock together so you don't get any heat loss through the joints. And that makes a major contribution to saving the amount of fuel you need to run the whole station. Now we heat the station by using heat which is captured off the generators, which are creating generous electricity for all the science experiments. We use that heat to then heat up the station in those places where it's necessary. But in many of the places you get enough heat just from the equipment that's running there anyway, and because there's such good levels of insulation we don't lose it, so we barely need any heating.
You use fuel for energy in the station. You've also tried using wind energy.
Actually, we haven't tried using wind energy, but we would really like to. But there's a big issue. Because the building is founded on an ice shelf, you can't get a decent enough foundation for your wind turbines. And so when you get the big gusts of wind, which can blow at maybe 150 kilometres an hour, you run the risk of the wind literally ripping the blades off the wind turbine. The Germans at Neumayer station, which is not very far away from Halle, only a few hundred miles, it has a wind turbine, but it's a 20 kilowatt turbine that they can only run at about 2 or 3 kilowatts of capacity, exactly because of that risk of, if they run it at full speed, then it will potentially just get shredded by the high winds. We've also looked at using photovoltaic and solar thermal panels. They're great, of course, but you know, when it's dark for a third of the year, they only work for a short period. But nonetheless, your electrical demand is often greatest in the summer when there are more people on the base, and I think it will only be a matter of time before those properly do get installed.
These buildings are very expensive. What do you have to keep in mind from an architectural point of view? For example, using the space in the station very well.
Yes. It's true. You know, the British station, even in terms of construction cost, probably costs around 14,000 euros per square metre, which is an enormous amount compared to a normal building anywhere else in Europe. So you have to be very careful that the space is used to the maximum advantage. So, for example, in our bedrooms, which we designed, we have used every single little nook and cranny for storage. So there's storage under the beds, behind the bed head, there's a lift-up flap so people can put things away. And we really carefully thought about what's the minimum dimension between beds and desks, within corridors, and so on. But we didn't want it to be mean, so there's a kind of balance between saving space and nonetheless having the sense of spaciousness, which doesn't necessarily always mean wasting it. It probably means utilising things like natural light and volume to your best advantage.
What was the greatest challenge in designing this place?
You know, there were so many different challenges, but I think logistics has definitely been one of the greatest ones, because, you know, ideally you would just prefabricate these buildings, deliver them to the ice and connect them together, and there's your job done. But we had the problem that everything had to be delivered onto sea ice rather than to the ice shelf.
Could you then please tell me about the other stations that you have looked at in Antarctica?
Yes. Well, some we've been asked to prepare designs for, but they've not necessarily been developed. But the one that definitely has been developed is a design we prepared for the Spanish, which is for a station on Livingston Island. It's a summer-only station. Livingston Island is a phenomenally beautiful location. It's off the Antarctic Peninsula with beautiful mountains, large penguin and seal colonies. And for that station, it came with a whole range of different challenges. It doesn't need to be relocated. The wind, however, blows in every single direction. There's risks of massive drifting no matter what orientation you give the building. And then added to that, the site has a number of very rare mosses, and so the building foundations had to be very carefully placed to avoid any of these moss beds. We've also looked at designs for Korea, for a new station on Terra Nova Bay. That also was interesting because the Koreans were particularly interested in how we could fuse some elements of Korean culture into the project. There are two strands to that, one of which is when you have buildings in cold regions, if they're near the surface, then you want them to be in line with the wind, and if they're high up, you want them to be perpendicular to the wind. So with that in mind, we then started looking with some Korean partners at potential cultural references for this new station. And we settled on the idea of the gateway, which has a very important part to play in Korean architecture because it symbolises the notion of passing through and of progress, passing through to something better. So we used the idea of gateway and then fused that with this idea of buildings close to the ground being in line with the wind and buildings being at high level being perpendicular to the wind to place the social module almost like a bridge, bridging between the living and the science spaces, but then also creating a gateway which is a symbol of Korean development, progress and Korean aspiration in the polar regions. I found that quite an exciting process actually, and something that some of the other projects hadn't demanded was that clear expression of national identity, but which was a very important part of the Korean project. So yeah, nice. We've looked at concepts for a more mobile building for India, and we've now just started working in the Arctic as well for the US program, where our first project is designing them a laboratory in what's called a clean air sector, which is where they take samples of the air and the snow as a benchmark for levels of pollution elsewhere on the globe.
So that's a different kind of challenge.
It is, because although it has some of the issues related to Halley in terms of rising snowfall and freezing temperatures and high winds, now we also have to have every material tested to make sure it's not going to have any residual gases being given off which might in some way impact upon the science. And that's a big challenge.
Could some of your designs even develop into homes for regular people?
I think absolutely. There's a lot of lessons in terms of the design of the outsides, in terms of aerodynamic, in terms of foundation design, in terms of levels of insulation, which could technically feed into a sort of mass market for housing, particularly in cold regions. But But I think also it's this idea that when you're designing in cold regions, you don't have to only produce functional architecture. You can produce places which are just as exciting to live in as they would be in mainstream society. And I think hopefully what this work that we've been doing in polar regions can do in some small way is to encourage people that human factors, space, light, those key ingredients of any kind of architecture have just as equal part to play in the polar regions as they do anywhere else in the world.
Can you make any predictions for the future, for future architectural infrastructure and designing in places like Antarctica and the Arctic?
There's going to be increasing pressure on designing buildings which have less and less reliance on fossil fuel as an energy source. And we're still a long way away from that, but there are some fantastic inroads that actually have probably been made by designs for other countries. The Belgium station, for example, which is zero carbon emission, utilises wind and solar power, and the Australians also have made some fundamental progress in using wind as the primary source of energy on some of their stations. I think at Mawson they now have 70% of their energy now generated using wind power, and I can see that definitely combined with higher levels of insulation and lower levels of air infiltration. Those three factors, bolt-on technologies, insulation, and low in air infiltration will combine to create really super energy efficient buildings, which is kind of in line anyway with global reactions to global warming.